and welcome to episode 9 of Maths in an Empty Classroom with me, Mr. Southern. What we're looking at today is the second example on hinges, and bit of a health warning, this one, proper gangster. So, let's just get straight into it. What we have is a uniform pole, AB, of mass M and length 6A, is freely hinged to a vertical wall at one end A. The pole is held in equilibrium in a horizontal position by a light rod CD. One end C of the rod is fixed to the wall vertically below A. The other end D is freely jointed so that AD equals 2A. Right, so let's just have a look first of all at getting this into a diagram. So, what I've actually done with this one is provided one. So AB is the uniform plank, and if we just remind ourselves what's happening here, it is freely hinged to a vertical wall at one end A. So the hinge is at A. Hinges at A. This is our uniform plank. What we have here is the light rod CD. C is fixed to the wall and it's joined to D, freely jointed, so that AD equals 2A. So the distance from A to D is 2A as labelled on the diagram. Freely jointed like so. Okay, so this is the scenario we've got. We've got a little bit of extra information to add to this diagram. Firstly, angle ADC equals alpha, where tan alpha equals 4 over 3. So let's label that on. Angle ADC is alpha, and we're told that tan alpha equals 4 over 3. Now, I've gone through how to do this in previous videos on connected particles, so I won't go through the whole thing again, but if tan alpha is 4 over 3, we know that sine alpha is 4 over 5, and cos alpha is 3 over 5. So that's the information we can get from the fact that tan alpha is 4 over 3. There was one more thing to consider here, which is a mass of 2n is attached to the pole at E, where BE equals x metres. So I need to add the point E onto my diagram, label the fact that that is x metres away, and it had a mass of 2m, so let's get straight on and label that force as being 2mg. Right, now let's consider other forces that are going to be acting on this system. The mass of the pole is m, and it's uniform, so that's going to act halfway along our system. So we draw a point in here that's halfway, and we label a weight going vertically downwards of mg. So we've got that force there. CD is a light rod. Now what's happening here is this plank is being supported by the rod. So if you think if the rod wasn't there to support the plank, what would happen? Well, the plank would swing down like this because it's hinged at A. What that means is the force that the light rod exerts on the plank, the tension must be going this way, although it's not in fact tension, it's thrust. As mentioned, if you look at what part A is asking us for, it's asking us to calculate the thrust in CD. And the reason it's asking for that is because this is a thrust force that's acting into the plank from the rod. Similarly, we would have a thrust force there, which is the rod acting into the wall. So we've got those forces acting there on the system at the moment. What we've also got to consider now is that the particle is hinged, the plank, is hinged at A, which, as discussed in previous example, would mean that there is both a horizontal and a vertical component of the reaction force. Now, let's just have a think about what's happening there. What is happening is that the thrust in this rod is causing this plank to want to go this way, like so. And what that means, in fact, is that the reaction force, or the horizontal component of reaction force, is actually going this way. That may make more sense when we actually come to resolve. And then the vertical component of that reaction is going this way. So labelling, as in the previous videos or video, reaction X, reaction at Y. Right, check the question. Mass M, I've dealt with that. 6A, we've got equilibrium horizontal position, light rod, 1NC is fixed, D is freely jointed, we've got alpha, we've dealt with tan alpha being 4/3, we've got the mass of 2m, and we've labelled BE as being x metres. Lovely. So what we're now doing is looking at calculating the thrust in CD in terms of X, A, M and G. So, let's have a look at how we would do that. Well, first off then, we are trying to find this force here, the magnitude of this thrust. We've got our three things that we can do as we normally would. We could resolve vertically, resolve horizontally, or we could take moments. Now what I'm going to do here to start with, I'm going to take moments about the point A, because then I can ignore the components of the reaction force, which at the moment I don't know. So I'm going to say my starting approach for part A is to take moments about A, and I need to think about any forces that are causing the plank to want to rotate clockwise. And there's two of them. One is this mg, which is a distance of 3a away, uniform rod, so it's halfway. So I've got mg times by 3a. And I've also got this force here, 2mg times by, now this distance here, from A to E, is going to be 6a minus x. Because the whole thing to B would be 6a, take off the x. So I've got 2mg times by 6 minus x. And they are the two forces that are trying to make this plank rotate in a clockwise direction. The force that's trying to make it rotate about here in an anti-clockwise direction is this thrust, which is trying to cause this force here. Now you'll remember in the previous example what I did was I drew on the component of that force this way here. And that force there, if you think about this angle here being alternate with that one, would be T sine alpha. So that force there is going to be T sine alpha times by 2a, which is the perpendicular distance from the line of action of the force. Okay. 2 sine alpha times by 2a. Lovely. Now, I know that sine alpha is 4/5 because I've just worked that out from my triangle, so I'm going to incorporate that in there in a minute. So what I have is 3a mg plus, expanding this out, 12 mg now that's 6, it should be 6a, shouldn't it? Which is going to affect this, so let's just change that. So I've got 12 A mg minus 2 mgx equals T times by sine alpha we said was 4/5 times by 2a. Right, so I've got 15 AMG minus 2mgx is equal to, now 4/5 times 2, that's 1.6. 1.6 AT. And we're being asked to find the tension in terms of A, M, G and X, so it's okay that I still have those 4 unknowns in there. Well, G is known, G is 9.8, but we've been asked to leave it in terms of G. So I can divide all of that by 1.6A, and I get that T is 15 AMG minus 2mg all over 1.6a, which is fine, but I don't especially like the fact we've got a decimal in the denominator of a fraction, so I'm going to multiply the numerator and the denominator by 5, which is going to give me 75 AMG minus 10 mg all over 8a for my tension. I've lost the x. There we go. Cool. Right, so moment equation done.